The Theory of Quantum Mechanics, a deeper dive into the subatomic world. Introduction. Picture a world where the rules of reality bend and twist in ways that defy our everyday experience. A realm where particles can exist in multiple states at once, where observing something fundamentally alters its behavior, and where the very fabric of existence seems to dance to a probabilistic tune. This is the extraordinary domain of quantum mechanics, a groundbreaking theory in physics that has revolutionized our understanding of the universe at its tiniest scales. In this detailed exploration, we'll journey through the origins of quantum mechanics, unpack its core principles with greater depth, and examine its far-reaching implications for science, technology, and even philosophy. Whether you're a science enthusiast or simply curious about the mysteries of the universe, this deep dive will take you into the heart of the subatomic world where the impossible becomes not just possible, but inevitable. Let's embark on this adventure into the quantum realm where reality itself is stranger than fiction. The birth of quantum mechanics. The story of quantum mechanics begins at the dawn of the 20th century, a time when classical physics, built on the sturdy foundations of Isaac Newton's laws of motion and James Clerk Maxwell's equations of electromagnetism, reigned supreme. Classical physics excelled at explaining the motion of planets, the trajectory of a thrown ball, and the behavior of light and electricity on a macroscopic scale. But as scientists began probing the microscopic world of atoms and subatomic particles, cracks in the classical framework started to appear, setting the stage for a scientific revolution. The first crack came in 1900, the problem known as the ultraviolet catastrophe. Physicists were studying black-body radiation, the light emitted by a heated object, like a glowing piece of metal. Classical physics predicted that a black body should have energy across all frequencies, with the intensity increasing infinitely at higher frequencies, shorter wavelengths, like ultraviolet light. This prediction was catastrophic because it contradicted experimental observations, which showed that the energy emission peaked at a certain frequency and then dropped off. German physicist Max Planck resolved this paradox by proposing a radical idea. Energy isn't emitted continuously, as classical physics assumed, but in discrete packets, which he called. Planck introduced a constant, now known as Planckston H, 6.6266 1034 Gs, to describe the size of these energy packets, suggesting that the energy of a quantum is proportional to the frequency of the radiation EHE, where I is the frequency. Initially, Planck viewed this as a mathematical trick to fit the data, but it marked the birth of quantum theory, earning him the Nobel Prize in 1918. The quantum idea gained further traction in 1905, when Albert Einstein applied it to another puzzling phenomenon, the photoelectric effect. When light shines on a metal surface, it can eject electrons, but classical physics couldn't explain the experimental results. According to classical theory, the energy of the ejected electron should increase with the light's intensity brightness, but experiments showed that the energy depended on the light's frequency color, and there was a threshold frequency below which no electrons were emitted, regardless of intensity. Einstein proposed that light itself is made of quanta, particles of light he called photons, and that each photon's energy is given by Planck's formula, EE. When a photon strikes an electron in the metal, it transfers its energy. If the energy is above the threshold needed to overcome the metal's binding energy called the work function, the electron is ejected. This explained the frequency dependence perfectly. Higher frequency light like blue has more energetic photons than lower frequency light like red. And increasing intensity simply means more photons, not more energy per photon. Einstein's work on the photoelectric effect, which earned him the Nobel Prize in 1921, solidified the quantum concept as a fundamental property of nature, not just a mathematical fix. The 1910s and 1920s saw quantum theory evolve rapidly as more scientists tackled the mysteries of the atom. In 1913, Danish physicist Niels Bohr developed a model of the atom that incorporated quantum ideas. At the time, scientists knew that atoms consist of a positively charged nucleus surrounded by negatively charged electrons, but classical physics predicted that electrons should spiral into the nucleus due to electromagnetic attraction, emitting continuous radiation and causing the atom to collapse. Bohr proposed that electrons orbit the nucleus in specific, stable energy levels, much like planets orbiting the sun, but with a quantum twist. Electrons can only occupy these discrete energy levels, and they transition between them by absorbing or emitting a quantum of energy, a photon with an energy equal to the difference between the levels de Te here. Bohr's model successfully explained the spectral lines of hydrogen, specific wavelengths of light emitted when electrons drop to lower energy states, and provided a stepping stone for quantum mechanics. Though it couldn't fully account for more complex atoms, the next leap came in 1924 when French physicist Louis de Broglie introduced the concept of wave-particle duality. De Broglie proposed that if light, traditionally thought of as a wave, your heart can behave as particles, photons, then particles like electrons might also exhibit wave-like behavior. He derived a relationship for the wavelength of a particle, or hop, where A is Planck's constant and P is the particle's momentum. This idea was experimentally confirmed in 1927 by Clinton Davison and Lester Germer, who showed that electrons diffracted off a crystal lattice, producing an interference pattern just like light waves. De Broglie's wave-particle duality became a cornerstone of quantum mechanics, blurring the line between particles and waves. By the mid-1920s, quantum mechanics took its modern form through the work of two brilliant minds, Werner Heisenberg and Erwin Schrödinger. In 1925, Heisenberg developed the first mathematical framework for quantum mechanics, known as matrix mechanics. Working with Max Born and Pascual Jordan, Heisenberg abandoned classical concepts like precise orbits and instead described quantum systems using matrices, mathematical objects that encode the probabilities of transitions between states. This approach was abstract and challenging but accurately predicted atomic behavior. A year later, in 1926, Schrödinger introduced an alternative formulation, wave mechanics. Inspired by de Broglie's wave hypothesis, Schrödinger developed the Schrödinger equation, a differential equation that describes how the wave function of a quantum system evolves over time. The wave function, denoted m, contains all the information about a system, and its square O2 gives the probability of finding a particle in a particular state. Schrödinger's equation was more intuitive than Heisenberg's matrices, and the two approaches were soon proven to be mathematically equivalent, providing a unified foundation for quantum mechanics. Together, these developments marked the birth of a new era in physics, one that would challenge our understanding of reality itself. Core principles of quantum mechanics. Quantum mechanics is governed by a set of principles that defy classical intuition, revealing a world where uncertainty, probability, and interconnectedness reign supreme. Let's explore these principles in greater depth, examining their experimental foundations and theoretical implications. Wave-particle duality. At the heart of quantum mechanics lies the concept of wave-particle duality, which states that entities like electrons, photons, and even larger particles can exhibit both particle, like in wave-like behavior depending on how they're observed. This principle was vividly demonstrated in the double-slit experiment, first performed with light by Thomas Young in 1801 and later with electrons in the 20th century. In the experiment, a beam of electrons is fired at a barrier with two narrow slits. On the other side of the barrier is a screen that records where the electrons land. If one slit is open, the electrons form a single band on the screen, behaving like particles passing through a hole. But with both slits open, the electrons create an interference pattern, a series of light and dark bands, indicating that they've interfered with each other like waves. This pattern persists even if electrons are sent one at a time, suggesting that each electron somehow passes through both slits simultaneously, interfering with itself as a wave. However, if you place a detector at one of the slits to determine which path the electron takes, the interference pattern disappears and the electrons form two bands, as if they've reverted to particle behavior. This experiment underscores a profound truth. The act of measurement in quantum mechanics determines the nature of the system, a phenomenon that challenges our classical notions of objective reality. Superposition. Quantum systems can exist in a superposition of multiple states at once, meaning they don't have a definite state until measured. For example, an electron in an atom can be in a superposition of two energy levels, simultaneously occupying both until a measurement forces it into one state or the other. This principle was experimentally confirmed in the 1970s through studies of atomic systems, such as the superposition of spin states in electrons or photons. A famous thought experiment, Schrödinger's cat, illustrates superposition on a macroscopic scale. A cat in a sealed box is linked to a quantum event like the decay of a radioactive atom that could either release poison, killing the cat or not. Until the box is open, the cat is in a superposition of being both alive and dead, a concept that highlights the high counterintuitive nature of quantum mechanics. Superposition is not just a theoretical idea, it's the basis for quantum computing, where quantum bits qubits can represent 0 and 1 simultaneously, enabling parallel computations that classical computers can't achieve. Quantum entanglement. Quantum entanglement occurs when two or more particles become linked in such a way that their states are interdependent, even across vast distances. For example, if two electrons are entangled, measuring the spin of one electron, e.g., QUP instantly determines the spin of the other, e.g., down, regardless of the distance between them. This phenomenon was first described by Einstein, Boris Podolsky, and Nathan Rosen in 1935 in a paper that challenged quantum mechanics, arguing that it must be incomplete because it allows for spooky action at a distance. Einstein believed that there must be hidden variables, unseen properties, that predetermine the particle's states, preserving classical notions of locality, the idea that objects are only influenced by their immediate surroundings. However, in 1964, physicist John Bell formulated Bell's theorem, which provided a way to test whether quantum mechanics or hidden variable theories were correct. Experiments, starting with John Clauser and Stuart Friedman in 1972 and continuing with more precise tests in the 1980s and 1980s by Aspect and others, consistently confirmed quantum mechanics. Entangled particles exhibit correlations that violate Bell's inequalities, proving that their states are truly interconnected in a non-local way. Entanglement has since been harnessed for applications like quantum cryptography, where it ensures secure communication, and quantum teleportation, where the state of a particle is transmitted instantaneously to another. The uncertainty principle. In 1927, Werner Heisenberg introduced the uncertainty principle, a fundamental limit on our ability to measure certain pairs of properties simultaneously. The most famous example is position and momentum. The more precisely you measure a particle's position x, the less precisely you can know its momentum p, and vice versa, mathematically. This is expressed as doxme PL2, where y is the reduced Planck's constant L2 This isn't due to limitations in our measuring tools, but is an intrinsic property of quantum systems arising from their wave-like nature. For instance, a particle's position is described by a wave function, and a well-defined position corresponds to a wave packet with a narrow spread in space, but a wide spread in momentum, since momentum is related to the wave's frequency via de Broglie's relation, P-Hall. The uncertainty principle also applies to other pairs like energy and time T equals YU2, which explains why particles can briefly borrow energy to exist in virtual states, a phenomenon critical to quantum field theory. The uncertainty principle shattered the classical dream of a deterministic universe where every property could, in theory, be known with infinite precision and introduced a fundamental randomness into nature, wave function, and probability. The state of a quantum system is encapsulated in a mathematical object called the wave function, denoted L, which evolves according to the Schrödinger equation. The wave function is a complex valued function that contains all possible information about the system, such as the probability of finding a particle in a particular position or state. Specifically, the square of the wave function's magnitude, mu2, gives the probability density of the particle's location. For example, in the double slit experiment, the wave function describes the probability of an electron landing at different points on the screen, producing the interference pattern. When a measurement is made, say detecting the electron's position, the wave function collapses to a single state a process that's still not fully understood. This collapse is central to the measurement problem in quantum mechanics. Why does measurement cause the system to choose one outcome? The Copenhagen interpretation, developed by Bohr and Heisenberg, posits that the wave function represents our knowledge of the system and collapse occurs upon measurement, but other interpretations, like the many worlds interpretation, suggest that all possible outcomes occur in separate, branching universes. The probabilistic nature of quantum mechanics means we can't predict exact outcomes, only the likelihood of different results, a stark departure from the deterministic predictions of classical physics. Implications and applications. Quantum mechanics has not only deepened our understanding of the universe, but also sparked a technological revolution that continues to shape our world. Let's explore its implications and applications in greater detail, highlighting both its scientific impact and practical contributions. Understanding the universe. Quantum mechanics is the key to understanding the behavior of matter at the atomic and subatomic levels, providing the foundation for much of modern physics, chemistry, and biology. In chemistry, quantum mechanics explains the structure of the periodic table and the nature of chemical bonds. For example, the Pauli exclusion principle, a quantum rule, states that no two electrons in an atom can occupy the same quantum state, which determines how electrons fill atomic orbitals and why elements have distinct chemical properties. In biology, quantum effects play a role in processes like photosynthesis, where plants use quantum coherence to efficiently transfer energy, and in the sense of smell, where quantum tunneling may help molecules interact with receptors. In astrophysics, quantum mechanics governs the nuclear fusion reactions that power stars, such as the proton-proton chain in the Sun, where quantum tunneling allows protons to overcome electrostatic repulsion and fuse. Quantum mechanics also explains exotic phenomena like superconductivity, where certain materials conduct electricity with zero resistance at low temperatures due to the formation of Cooper pairs, pairs of electrons that move in a coordinated quantum state. Technological advancements. Quantum mechanics has given rise to technologies that define the modern era, many of which we take for granted. Semiconductors, the backbone of electronics, rely on quantum principles like the band theory of solids, which describes how electrons occupy energy levels in a material, enabling the creation of transistors and microchips that power computers, smartphones, and countless devices. Lasers, which produce coherent light through a process called stimulated emission, a quantum phenomenon where an incoming photon causes an excited atom to emit a second photon of the same frequency, are used in applications ranging from barcode scanners to fiber optic communication to precision surgery. Medical imaging technologies such as magnetic resonance imaging MRI and positron emission tomography PET depend on quantum effects. MRI uses the quantum spin of hydrogen nuclei to create detailed images of the body, while PET relies on the annihilation of positrons and electrons, a process governed by quantum mechanics. Even the Global Positioning System GPS owes its accuracy to quantum mechanics, as the atomic clocks that synchronize GPS satellites operate using quantum transitions in cesium atoms. Quantum computing. One of the most promising frontiers of quantum mechanics is quantum computing, which leverages quantum principles to perform computations in ways that classical computers cannot. Classical computers use bits to represent information as either 0 or 1, but quantum computers use quantum bits or qubits, which can exist in a superposition of 0 and 1 simultaneously. This allows quantum computers to process a vast number of possibilities at once, making them potentially exponentially faster for certain problems. For example, Shor's algorithm, a quantum algorithm developed in 1994, can factor large numbers of tasks critical for cryptography much faster than classical algorithms, posing a few challenge to current encryption methods like RSA. Quantum computers also excel at simulating quantum systems, which could revolutionize drug discovery by modeling complex molecules and optimizing problems, such as finding the most efficient routes for logistics or designing new materials for renewable energy. Companies like IBM, Google, Microsoft, and startups like D-Wave and Rigetti are making significant strides in quantum computing, with Google claiming quantum supremacy in 2019 by performing a calculation in 200 seconds that would take a classical supercomputer 10,000 years, though this claim is debated. However, quantum computers face challenges like decoherence, where qubits lose their quantum state due to environmental interference, and error correction, which is more complex than in classical systems. Despite these hurdles, quantum computing holds the potential to transform industries and solve problems previously thought intractable. Philosophical questions. Quantum mechanics doesn't just challenge our scientific understanding, it raises profound philosophical questions about the nature of reality, observation, and free will. The measurement problem, for instance, asks why the wave function collapses upon observation and what constitutes a measurement. The Copenhagen interpretation, developed by Bohr and Heisenberg, argues that the wave function represents our knowledge of a system, and collapse occurs when we measure it, implying that reality is indeterminate until observed. This view suggests that observation plays a fundamental role in shaping reality, a concept that some find unsettling. In contrast, the many worlds interpretation, proposed by Hugh Everett in 1957, posits that the wave function never collapses. Instead, all possible outcomes of a quantum event occur, each in a separate, branching universe. In the case of Schrödinger's cat, this means the cat is alive in one universe and dead in another, and both universes are equally real. Other interpretations, like the de Broglie-Bohm theory, introduce hidden variables to restore determinism, suggesting that particles have definite positions guided by a pilot wave. Though this theory struggles to explain non-locality, quantum mechanics also challenges our understanding of causality. Entanglement implies that events can be correlated instantaneously across vast distances, violating classical notions as of locality and raising questions about the nature of space and time. These philosophical debates are not just academic, they influence how we interpret experimental results and design future technologies, such as quantum computers that rely on superposition and entanglement. Challenges and future directions. While quantum mechanics has been extraordinarily successful, it's not without its challenges, particularly when it comes to reconciling it with other fundamental theories and addressing unresolved questions within the theory itself. Let's explore these challenges and the future directions of quantum research in greater detail. One of the biggest challenges is the incompatibility between quantum mechanics and Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe. Quantum mechanics excels at describing the behavior of particles at small scales, while general relativity governs the cosmos, planets, stars, and black holes. However, the two theories operate on fundamentally different principles. Quantum mechanics is probabilistic and non-local, while general relativity is deterministic and local, with gravity described as the curvature of spacetime. When we try to apply quantum mechanics to gravity, such as in the extreme conditions near a black hole or during the Big Bang, the equations break down, producing infinities that can't be resolved. This has led to the search for a theory of everything that unifies quantum mechanics and general relativity. String theory, one of the leading candidates, proposes that particles are not points but tiny vibrating strings, and that gravity is mediated by a particle called the graviton. Another approach, loop quantum gravity, attempts to quantize spacetime itself, suggesting that space is made of discrete loops at the Planck scale 10^35 meters. Both theories are promising but lack experimental confirmation, as testing them requires energies far beyond our current capabilities, such as those found in the early universe or near a black hole. Another unresolved issue is the measurement problem, which we touched on earlier. Why does the wave function collapse upon measurement, and what triggers this collapse? The Copenhagen interpretation offers a practical solution but doesn't explain the underlying mechanism. Some physicists, like Roger Penrose, suggest that gravity might play a role in wave function collapse, a hypothesis being tested through experiments that look for quantum effects in macroscopic objects. Others explore objective collapse theories, which propose that collapse occurs spontaneously at a certain scale, independent of observation. These questions are not just theoretical. They have practical implications for quantum technologies, where near harm, maintaining superposition and entanglement is critical. Looking to the future, quantum mechanics is poised to unlock new frontiers in science and technology. Quantum cryptography, for example, uses entanglement to create unbreakable encryption methods such as quantum key distribution QKD. In QKD, two parties share an entangled pair of particles to generate a secret key. Any attempt to intercept the key disturbs the entanglement. Alerting the parties to an eavesdropper, China has already demonstrated QKD over long distances using the MISHA satellite, paving the way for a global quantum internet. Quantum sensors, which exploit quantum effects like superposition and entanglement, could revolutionize fields like navigation, GPS-independent systems using quantum gyroscopes and medical diagnostics, e.g., detecting magnetic fields in the brain with unprecedented precision. Quantum computing, as mentioned earlier, continues to advance, with researchers working to over challenges like decoherence and scaling up the number of qubits. In the coming decades, quantum computers could tackle problems like optimizing global supply chains, designing new materials for clean energy, and simulating complex biological systems for drug discovery. Beyond technology, quantum mechanics is driving new experiments to test its foundations. For example, researchers are exploring the role of gravity in quantum systems, such as by placing massive objects in superposition to see if gravitational effects cause wave function collapse. Other experiments aim to push the boundaries of entanglement, such as entangling particles over greater distances or even entangling macroscopic objects. These efforts could shed light on the nature of quantum reality and potentially reveal new physics beyond the standard quantum framework. Conclusion: quantum mechanics is a testament to the power of human curiosity, revealing a universe that is far more intricate and mysterious than we ever imagined. From its origins in the early 20th century with Planck's quanta and Einstein's photons to its formalization by Heisenberg, Schrödinger, and others, quantum mechanics has transformed our understanding of the subatomic world, challenging our classical notions of reality and opening up new realms of possibility. Its core principles, wave-particle duality, superposition, entanglement, the uncertainty principle, and the probabilistic nature of the wave function, paint a picture of a universe where uncertainty and interconnectedness are fundamental, where observation shapes reality, and where particles can be linked across vast distances in ways that defy classical logic. The implications of quantum mechanics are vast, from explaining the behavior of atoms and molecules to powering technologies that define the modern world. Like semiconductors, lasers, and MRI machines, it has given rise to emerging fields like quantum computing, which promises to revolutionize computation, and quantum cryptography, which should secure our digital future. At the same time, quantum mechanics raises profound philosophical questions about the nature of reality, the role of observation, and the structure of the universe, fueling debates that can continue to inspire scientists and thinkers alike. As we look to the future, quantum mechanics remains a field of immense potential and mystery. The quest to unify it with general relativity, resolve the measurement problem, and harness its principles for new technologies will drive scientific discovery for decades to come. Whether it's unlocking the secrets of the cosmos, building the next generation of computers, or redefining our understanding of existence, quantum mechanics will continue to push the boundaries of what we believe is possible. So the next time you hear about a particle being in two places at once, or two particles sharing an unbreakable bond across the universe, remember, you're witnessing the magic of quantum mechanics, a theory that has not only reshaped our world, but also revealed the profound strangeness at the heart of reality itself.
Quantum Stellar needs your help to make this content possible. Your contributions are greatly appreciated. Thank you.